Okay, welcome to what would be week 11 in review now, and this is the first video that I'm going to produce for level 3 thermochemistry. I'm calling it thermochemistry part 2 because you also studied thermochem in level 2 last year, which would have been part 1. Now, in order to introduce any new part to a course, there's also always some key terms that you have to cover. So the main key terms, first of all, with thermochemistry is, I'll just do a quick definition here. For thermochem, I would say is that part of chemistry. So the part of chemistry which looks at the overall heat loss or gain for a chemical reaction. Okay, so that would be my general definition of thermochemistry. It's the part of chemistry which looks at the overall heat loss or gain for a chemical reaction. Then there's some key symbols that we need to introduce. Delta or E, that represents the change in heat energy. So it's heat energy that we're talking about here for a reaction. And the units of energy, as you hopefully remember from level 2, would be joules, which I always tell my students to convert straight away to kilojoules. Now, delta RH is not the same as delta RE. Okay, delta RH is the enthalpy change. The enthalpy change for a reaction, and it's per mole of substance of interest. So this is the difference between delta RH and delta RE, or in the difference between enthalpy and energy. Okay, so the enthalpy for a reaction, the units of that, since it's the enthalpy change or energy change. Let's just redefine that because I didn't define that the way I'd like to. So if I redefine that as the energy change for reaction per mole of substance, then instead of the units just being kilojoules, the units are going to now be kilojoules per mole. So the main difference between enthalpy and energy is that enthalpy is the energy change per mole of substance. So the units of enthalpy will be kilojoules per mole, whereas the units of energy will be just kilojoules. And that's something that students often mix up, so make sure you get that right. And then we have another symbol that you can use, which is delta RH with a superscript or a small zero there. And this is the enthalpy change for a reaction carried out under standard conditions. So we referred to this before when we were looking at um, reduction potential values in redox chemistry, and we had standard reduction potential values in a big table. And the same situation here, that these experiments are carried out under standard conditions, which would be 101.3 kilopascals of pressure, or 1 atmosphere of pressure, 25 degrees Celsius, and you're also using 1 mole of the substance at all times. So not all your exam questions will necessarily refer to enthalpy, which is measured under standard conditions, but if you see this zero, then you need to be aware of that, and it's important for some types of reactions like combustion, where you can assume that there's complete combustion taking place. Now, if we look at the identity of R here, R just represents any reaction. Now, the 4 main types of reaction that you'll come across in level 3 will be a combustion reaction. So R can be combustion, it can be formation of a compound, it can be fusion, which we would also know it as melting, and R could also be vaporization. Vaporization, which we could also refer to as boiling. All right. So if we look at each one of these entities now, these possible reaction types, and just take a quick look at what the definition is for each of those. Delta CH, so now we're replacing R for C for combustion. this is the heat of combustion of 1 mole of a substance. Now, they don't typically ask you to define things on your level 3 assessments, or even level 2 for that matter, but what they will assess you on is they'll give you a certain fuel, in this case hexane, and they'll say write the equation for the enthalpy of combustion of that fuel. So what you need to always remember is that if it's complete combustion, and you'll be able to tell that either by the little 0 at the top, or if the question says complete combustion, okay? If they say complete combustion, then the products of that reaction are always going to be carbon dioxide and water. Always, with complete combustion, you get carbon dioxide and water, and you have some fuel which is reacting completely with oxygen. So now all you have to do is make sure this equation is balanced. So if we take a look at our carbons, we need 6, so we put a 6 here, and then with our hydrogens we need 14, so we put a 7 there, and that gives us a total of 19 oxygens. So if we put a 9.5 here, then that should even up our oxygens, and that's our balanced equation. Now the temptation here is to get rid of these fractions by factoring across by 2. But if we look back to the definition for heat of combustion, we're looking at it per mole of substance. So we must keep it that we have 1 mole of hexane in this case. So that's why we don't alter the equation there at that stage. We keep it to 1 mole because that's what the definition says. Delta CH is a measure of the heat of combustion per mole of substance of interest. Okay, so that's delta CH. Then if we take a look at delta FH, so this is for formation. So this is the heat change as you form 1 mole of a substance from its constituent elements, so in other words the elements that make it up, constituent elements as they exist at room temperature and pressure. So again, it doesn't make a lot of sense until you look at a particular example. So if we take a look at the formation equation for ammonia, so ammonia is NH3. So the first thing you do is you write down what you're trying to form, which is ammonia. Now since you're forming it, that must be on the product side, so we can put our arrow pointing towards ammonia. And then the definition says it's the heat change as you form 1 mole of a substance, so make sure you keep it as 1 mole, from its constituent elements as they exist at room temperature and pressure. Well, the constituent elements of ammonia are obviously nitrogen and hydrogen. Now nitrogen, as hopefully we are all commonly aware of at this stage, exists as 2 atoms stuck together. It's a diatomic molecule. So that's how nitrogen exists at room temperature and pressure. And similarly, hydrogen is also diatomic, so you have 2 of them. So now we just need to make sure we balance the equation up. And again, don't be afraid to use fractions because we have to keep it to 1 mole of the substance of interest. So in this case, we're going to have to use 1.5 of the hydrogen molecules, and then half a mole of the nitrogen molecules. And that's your balanced equation. This would be written as the enthalpy of formation of ammonia. Okay. So then that's our second type of reaction we can take a look at. The third type of reaction you can take a look at is delta FUSH, so delta fuzz, or delta the enthalpy of fusion. So this is the heat required to melt 1 mole of a substance. So, simple terms, the heat required to melt 1 mole of a substance. And so if you were asked to write the enthalpy of fusion, so if your exam paper says write the enthalpy of fusion for water, and since it's melting, it's going to have to be starting off as a solid. It's a very simple equation. You literally write down H2O solid, and then it's changing to a liquid, which is what happens with melting. So that's what you write if you're asked to represent an equation for the enthalpy of fusion of water. And then the fourth possible reaction type we can be studying the enthalpy change for will be enthalpy of vaporization. So this is the heat change required to vaporize or boil 1 mole of a substance. So in this case, if you're asked to write the delta VAP for water being vaporized, in this case you're starting with a liquid, then it's going to be liquid water being heated to turn into gaseous water or water vapor. Just a note to make on some of these entities. So if we go back to the top here, because little things like this are nice to know when you're making calculations later on with these concepts. Delta CH, or enthalpy of combustion, is always negative. So delta CH for any combustion reaction will be negative kilojoules per mole overall. So it's an exothermic reaction. Combustion is a great example of an exothermic reaction. In the class we did a little demonstration with methane bubbles, and it's quite obvious that there's a lot of heat produced there in excess, which is a sign of an exothermic reaction. Enthalpy of formation can be positive or negative depending on the reaction type, so that can be positive or negative. Whereas enthalpy of fusion and enthalpy of vaporization, just use a different color here, give me red. So enthalpy of fusion, to melt something, is always going to have to involve adding heat to a system, so it's going to be a positive enthalpy change or an endothermic reaction. So it's always an endothermic reaction to melt something, and similarly to boil something is always going to be endothermic as well. So both of those are always going to be endothermic. So you need to make sure you check that when you're doing your calculation if associated with any of these reaction types. And the final thing just to say here with enthalpy of fusion and vaporization, enthalpy of vaporization is always greater than the enthalpy of fusion. And this is because when you boil something, you completely separate the particles. So I'll do this on a new page, just instead of being stingy with the space there. Get a new page. Okay, so quickly, just this is enthalpy of vaporization versus enthalpy of fusion. So with fusion or melting, you start off from a situation where you have a lot of particles which are closely packed together. That's your classic particle diagram for a solid. So this could be ice or solid water. And then you are breaking intermolecular bonds as you separate those particles out to make liquid. So liquid water or H2O liquid. But you don't completely break every single intermolecular bond. There's some of them which may be closely linked. There's a few might be separated, but in general, the particles are not completely separated in the liquid. They're just more loosely packed together. And as a result, you don't fully break all the intermolecular bonds. You don't fully break all the intermolecular bonds. Whereas if you're going to vaporize something, so you're taking it from that liquid situation where the particles are loosely packed and you want to make it into a gas, well, you need to completely separate all those particles. So you need to completely break the intermolecular bonds. Completely break the intermolecular bonds. And this is why it always takes more energy to vaporize something than it does to melt something. And that's just a little aside in discussing vaporization versus melting. It might be a question that would come up in the exam paper. Okay, so that was the general background. For a lesson, I also talked about the exothermic curve that you did last year for an exothermic reaction, and the endothermic curve that you did in level 2 as well. We looked at some examples of reaction types and got you guys to decide whether they were exothermic or endothermic. And then we started to take a look at the ways to actually calculate enthalpy for a reaction. So if we look at that now, so we're moving on to essentially the second lesson. which was how to calculate the way to calculate the enthalpy for a reaction. Now, the first way is from experimental data. First principles from experimental data. Second way is to use this formula. The enthalpy for a reaction can be found from taking the enthalpy of formation of the products and subtracting the enthalpy of formation of the reactants. That's a simple equation, but be aware of it. Sometimes you can use it and it makes calculation easier than doing it some of the more difficult ways, and you cover that in level 2. Number 3, you can calculate the enthalpy of a reaction by adding up the bonds broken and subtracting from that the bonds formed. And that's something that you covered in level 2. It was just introduced to the level 2 course last year, so we'll obviously review that, but it's expected that you have some background on that. And then the fourth way is to use Hess's law. Hess's law can get a bit tricky, but once you know how to do one example and you have a good understanding of delta CH, delta FH, delta FUSH, and delta VAP, you'll be able to do Hess's law and start to enjoy it. So what I'm going to do now is, on the last lesson of the week last week, in week 11, I just covered how to calculate delta or H from experimental data. So we're going to take a look at a question from the 2009 exam paper, and we'll just walk you through how to perform that calculation and talk a little bit about the theory behind it. Okay, so here's the 2009 question. I'm not sure what number it was, but it's part B, and the question is on calculating enthalpy for a reaction using an experiment. So the question says the apparatus below was used to determine the enthalpy of combustion of hexane when 0.400 grams of hexane were burned in the spirit burner. Spirit burner is just this little thing here. Make sure I get my pen here. So that's a spirit burner. The temperature of 150 grams of water in here, so you have 150 grams of water, was found to increase from 22 degrees Celsius to 39 degrees Celsius. So the increase in temperature here was an increase of 17 degrees Celsius. Now that tells you that it's an exothermic reaction, which we mentioned already. Combustion is always going to be exothermic. So you're going to have a negative delta CH value. That's the first thing you can infer from reading the question. What else can we talk about there? Calorimeter in thermochem is simply a reaction vessel plus a means to measure temperature. So in this case we have a thermometer. So in general terms, a calorimeter in thermochemistry is a reaction vessel where you put some sort of chemical inside it, and then you can measure the temperature change for the reaction. So here comes the question. Calculate the experimental value of delta CH, the enthalpy for combustion of C6H14, which is liquid hexane. You're also given the molar mass of hexane, which is 86.0 grams per mole, and you're given this thing here called the specific heat capacity of water, which is 4.18 joules per gram per degree Celsius. Now, it's always going to be the specific heat capacity of water when you look at these questions. So how do we do this? How do we approach these? So I'm going to just reduce the size of the page a little bit so you can see the question as I do it. I'm going to use a different colored pen here as well, just to highlight what I'm doing. So we'll go for a nice bright red there. Right, the first thing I want to do is I want to work out the energy change for the reaction. So delta or E calculated using this formula here. Now with formulae and exams, guys, you got to learn them off. You're not given any formula for level 3 chemistry or level 2 for that matter. So there's a certain level of rote learning that you have to do, and that's what it provides you guys with those posters for. I call this the MyCat formula because it looks like you're spelling out my cat. Where M stands for the mass of water. Please don't show this message again. Okay, so M stands for the mass of water which is present in this reaction. In this case, that's 150 grams from the question. C stands for the specific heat capacity of water, which it's always going to be given to you, so don't try to memorize this number, but you will start to come closer to your exams. It's 4.18 joules per gram per degree Celsius, And delta T obviously stands for the change in temperature for this reaction, which we said was 17 degrees Celsius, which came from 39 minus 22. And that was also given to you in the question. So if we do this calculation, we can work out that the change in energy for the reaction is 10,659 joules. And if we just keep track of our units there for a second, the degrees Celsius will cancel with the degrees Celsius from the 17. The grams, reciprocal grams, or grams to the -1 will cancel with the grams and the 150, which leaves your joules here, which transfer over to your final answer for energy change for the reaction. Now, as I said at the beginning of this video, I said anytime you get energy in joules, you should try to change to kilojoules straight away. So 10,659 joules is also 10.659 kilojoules. So you've worked out the energy change for the reaction. Now, students often think they're finished here with the calculation, and I made this point already. The energy change for a reaction is not the same as the enthalpy change for a reaction. Why would they invent a new parameter called enthalpy if they could do the same thing using energy change? So we're about halfway through this calculation. So the next key point is, how do you change from energy change for a reaction to enthalpy change for a reaction? Well, this is a little triangle I put together. Essentially, because enthalpy is the energy change per mole of substance, well, then this is the triangle that you want to use to make that conversion between the two. So we know delta RE is 10.659 kilojoules. So how do we work out the moles of hexane? Well, this is a throwback to level 2 calculations for quantitative chemistry. If you remember that you can work out the moles of any substance using this triangle. So this is the mass moles molar mass triangle. And if you want to work out the moles of hexane, in this case, C6H14, well, they've kindly given you the molar mass for hexane as 86.0 grams per mole. So to work out the moles of hexane, we want to take the mass, which were 0.400 grams, and that's from up here. 0.400 grams of hexane divided by the molar mass, which is 86.0 grams per mole. And that gives you a mole value of 0. I'll just write this in a bright color so you can see it. So the moles of hexane are 0. That yellow's terrible. Let's change that. And let's go with this pink. 0.0046511. Now, as we talked about before in level 2, if you keep those numbers as long as possible, essentially until the final answer, well, then you're maintaining accuracy. So that's quite a decent number of decimal places. So for the final calculation, we want to take 10.659 kilojoules and divide it by the 0.004651 moles, and that will give us a final answer of 2292 kilojoules per mole. We're not just finished yet. You must always put a sign in when you're quoting enthalpy change values, and in this case it's exothermic. It's a combustion reaction, so it's negative. And that's how you do that calculation. So basically there's two main steps or formulas that you need to use. You need to use the MICAT formula, followed by the delta RE, delta RH, and moles triangle. And that's the correct answer for that there. Now the question then just goes on to say, account for the difference between the experimental value that you record here and the value given in part A, and suggest how this difference could be minimized. So the value given in part A was not the same. It was much greater than this value we've just recorded here or calculated here. And the reasoning for that is essentially because it's not a robust experimental setup and it's not performed under standard conditions. So if I just quickly, I'll just jump to the sample answer for that part. So here we go. Heat loss to the surroundings, right? So it's heat being lost to the surroundings, so it needs better insulation, such as a lid on the beaker, lagging on the beaker, which would be like an insulation jacket, containment of the heat from the flame. So you can put up shields around your setup, and we noticed this when we were doing it in classroom. Even just general airflow in the classroom was causing the flame to move all over the place. As a result of this, incomplete combustion occurs, so you would have to ensure there were plenty of oxygen supplied, which is not something we want to be doing in a school lab because that's highly explosive. And number three, it's not done under standard conditions, so you would need to make sure that the room temperature was 25 degrees Celsius, you had 1 atmosphere of pressure, and that is the answer that you need to give when the exam paper asks you to how to improve your experimental setup. So if I just quickly draw a picture, let's go back here for a second. If I was to draw a picture of an improved experimental setup, I'll just grab a black here. So you would put some shields either side of your setup. Your beaker of water, you would put a lid on it, and then just have a little space for the thermometer to come out. So put a lid on top. They're also mentioned that you should use some insulation. So get some of that insulating material that you can and put it around your container. You could also, well, they're talking about having an ample supply of oxygen. So if you really wanted to go crazy, you could have some sort of way of introducing a plentiful supply of oxygen to make sure the combustion is complete, and make sure it's performed at 25 degrees Celsius and 1 atmosphere of pressure, etc. So it's a nice question to get in your exam paper, and that is an introduction to one of the 4 ways of calculating enthalpy for a reaction. So this is where we finished off here. So as far as I'm concerned, we've covered how to work out the enthalpy for a reaction using experimental data. And then now in the last week of term, week 12, we're going to look at these other 3 ways here. And we'll come back and do a video at the end of week 12.